Okay, here's part 2 to the Intro to related rates notes. I apologize. George and I both apologize for the slantedness of the first video, but we're trying to do the best that we can with what we have. So, just to review, related rates is the implicit differentiation with respect to time, and the derivative is the slope of the tangent line to a curve at a point, and slope is the rate of change. So on the related rates notes, it gives you like a summary of the first set of notes that we already did. So you can read through them, but really you don't need to. What you do need to highlight is this box right here, which is the guidelines for solving related rates problems. And you guys already have these notes. So and all they say is, they give you a procedure to solve related rates problems. Make a sketch and label the quantities, read the problem and identify all your quantities as what you're going to find, when and given. Write an equation involving the variables whose rates of change either are given or are going to be determined. Using the chain rule, implicitly differentiate both sides of the equation with respect to time. And after completing step 4, substitute into the resulting equation all known values for the variables and their rates of change, then solve for the required rate of change. Now, this is just a bunch of words, and it'll make more sense once we start going through the examples. So let's go through example 1, which says, suppose that x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. They want you to find dy dt when x is 3, given that dx dt equals 2 when x equals 3. So, what we do know is y equals x squared minus 3x. We're given dx dt when x equals 3 to be 2, and we need to find dy dt when x equals 3. So first we have to take what's known, find the derivative of both sides with respect to time. So dy dt equals 2x dx dt minus 3 dx dt. On the right side, we can factor out a dx dt. Now, we were given dx dt when x was 3 to be 2, so we can substitute that in. So dy dt equals 2 parentheses 2 times the x that we used for that 2 was 3 minus 3, and that's 6 minus 3 is 3, 2 on the outside, so really dy dt is equal to 6. And there's your answer to the first one. So let's keep going. Example 2. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what rate is the total area A of the disturbed water changing? So let me erase example 1. What will not change are the labels of what's given, what we know, and what we're trying to find. For this one, we can even set up a picture for it. So example 2, we dropped a pebble into a pond, and it's creating, the ripples are creating concentric circles. So when the radius is 4 feet, at what rate is the total area of the disturbed water changing? Well, we know the area formula for a circle is A equals pi r squared. We know that the radius has to be 4 feet. We're given that the rate of change of the radius of the outer ripple is increasing at a constant rate of 1 foot per second, and they want us to find the change in the area when the radius is 4. So again, we take our area formula, take the derivative of both sides. Remember that pi is just a constant, so you really have 2 pi r dr dt. Substitute in your given values. So dA dt equals 2 pi, radius is 4, dr dt is 1 foot. Well, sorry about this. Radius is 4 feet. So let me include that label there. 4 feet. Dr dt is 1 foot per second. All we have to do now is simplify it. So dA dt equals 8 pi feet squared per second. And that's it. And there's our answer for question, or example 2. Example 3. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon changing? At the instant, the radius is 30 centimeters. So let's draw a diagram for that one. Example 3. And we're looking for the radius being 30 centimeters. And we're looking for how fast it changes. Well, we know the volume of a sphere is 4/3 pi r cubed. We're given that the volume is changing with respect to time, being 800 cubic centimeters per minute. And we're asked to find the change in the radius over time when the radius is 30 centimeters. So, once again, take your known formula, take the derivative of both sides. 4/3 is just a constant, so 4/3, we really have 3r squared dr dt. We can simplify this to, the 3's will cancel out, and we're left with 4 pi r squared dr dt. Now we substitute in our known values. dV dt is 800 cubic centimeters per minute. That's equal to 4 pi. Our radius is 30 centimeters squared, and we're looking for dr dt. Okay, if we simplify this, on the right side we have 30 squared is 900. 900 times 4 is 3600 pi centimeters squared dr dt. That's still equal to the 800 centimeters cubed per minute, and we have to get dr dt by itself, which means dr dt equals 800 centimeters cubed per minute, and that's going to be divided by 3600 pi centimeters squared. And we can simplify this to 2 over 9 pi centimeters per minute. And that would be the answer to example 3. 2 more to go. Oh no! I lied. 4 more to go on related rates. Example 4. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? So let's draw a diagram of that. So we've got 25-foot ladder, and it's we know that the equation for a right triangle is x squared plus y squared will be, in this case, 25 squared. We're given that it's sliding down vertical wall at a constant rate of 3 feet per minute, and we're asked to find the distance between the bottom of the ladder and the wall, which in this case is either change in x over time when it's 7 feet from the ground, so when y is equal to 7. Okay, well first it would make more sense if we found x before we started anything else. Taking our known equation, we're going to say x squared equals 25 squared minus y squared. Well, 25 squared is 625 minus y in this case is 7 squared. So 625 minus 49. I'm not too sure what that is off the top of my head. But when we take the square root, x will equal to 24 feet. So x will equal 24 feet. And then we follow the same procedure that we've done before. We take our known equation and take the derivative of both sides with respect to time. And let's get dx dt by itself. So dx dt will equal to negative 2y divided by a 2x dy dt, which will then simplify to negative y over x dy dt. And this is what we're going to use to substitute in our values, which will be dx dt when x equals 24, when y equals 7, negative 7 over 24 times, we're given dy, so 3 feet per minute. We can simplify the 3 and the 24. 3 goes into 3 one time. 3 goes into 24 8 times. So this is really going to be negative 7 feet. Negative 7/8 of a foot per minute. There's the answer to example 4. Example 5 says, at noon, ship A is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So, again, let's draw a diagram. Here's ship A, here's ship B. Call this one Z, call this one Y, and this will be 150 minus the X. Now, what do we know? Well, again, it's a right triangle, so x squared plus y squared will be equal to z squared. We're given that ship A, which has a distance of x, it's traveling at 35 kilometers per hour. And ship B, which we'll call y, is traveling at 25 kilometers per hour. And we are asked to find the distance between the two when time is equal to 4 p.m. or after 4 hours, since it's talking about from noon to 4. So, just like with example, this is example 5. Just like with example 4, that we had to find the value of x before we began our procedure for related rates, we need to find x, y, and z before we actually begin the process. Well, x will be, after 4 hours, it's going 35 kilometers, so that's really 140 kilometers. Y will be 4 times 25, which is its rate, and that's 100 kilometers. Now for z, since it's in the form of a right triangle, we're going to take the square root of 140 squared plus 100 squared, which is really the square root of 29600. And we can simplify this to 20 times the square root of 74 kilometers. Now you can write out the decimal form, which is, I believe, 172 point something. But for this problem, just leave it in terms of the radical. So just like before, we're going to take our known and x squared is actually 150 minus x, the whole quantity squared. Now we take the derivative of both sides. So we really have two of these, because it follows the chain rule. Dx dt plus 2y dy dt equals 2z dz dt. From here, we're going to take the -1, we're going to multiply it by the -2. And let me follow this up here. So that's really -2 times 150 minus x dx dt plus 2y dy dt is equal to 2z dz dt. From here, you substitute in what you already know. It's -2, 150 minus x, which was 140. dz dt was 35, plus 2 times the y, which was 100, times 25, and that equals to 2 times 20 square root of 74 dz dt. Well, that's a lot, I know. So we're going to take the left side, we're going to simplify it. That actually becomes 4,300 equals 2 times the 20 is 40 square root of 74 dz dt. You want to get dz dt by itself, so you divide both sides. So you really have 4,300 divided by 40 square root of 74, which can then simplify if you divide by 20 to 215 over 2 square root of 74. You can plug that into the calculator, get the decimal approximation, but this is actually what you're looking for. Don't forget your units, which is kilometers per hour. you do have examples 6. Ooh. Examples 6 and 7. And I actually want you guys to try those two. On the next video, I'll give you the answers. And on Thursday when we meet up, if you guys have questions on that, then we'll go over it. But that's pretty much the same procedure for every single problem. If you notice through the 5 examples we've done, you used your known, find the derivative, plug in your givens so that you can find what they're asking you to find. And that's all related rates is. So we're done with related rates for now, other than examples 6 and 7, which you guys have to do on your own.